Thank you, and good morning, everyone. It's my pleasure to be here to present this work that takes place in international projects aiming to find some way to assist low vision people in their everyday life. We choose to obtain this assistance to low vision to use light. So why this work? This work is because according to the most recent review of the World Health Organization, there are a huge number of people that are living with a visual impairment worldwide, and more than 80% of these people were not concerned when they were younger by a visual problem. And today it represents, for these people, it represents around 300 million of people that are living with the problem of low vision. So I will not go back on the definition of low vision, just because the third speaker this morning clearly explained that. Also this work because the prediction, unfortunately, are not very good, because the number of visually impaired people are supposed to triple by 2030. The problem with as you can imagine, the problem with visual impairment is that quality of life can be dramatically affected. And for the moment, the visual aids are very simple. The main visual aids are based on magnifiers for reading, especially, and also on canes for the mobility. Of course, as we have seen previously, is that we have different electronic devices that can be proposed, but for the moment they have a lot of drawbacks, just because they cannot be. There's drawbacks, for example, in terms of the autonomy of the batteries and all these things, and. Some of them, they are not very efficient because you have to use one of your hands, so it's not very common when you want to manipulate some objects. And also, maybe the main drawback is that the visually impaired, they have to be trained to use these devices. So, in other words, these devices not adapt to the problem, but it's the patients that have to adapt to the assistive system. So, what we try to do is that, as we in the scientific literature, there are numerous papers that have demonstrated the importance of the color to identify objects. So the question that we wanted to investigate is: would it be possible to use the light characteristics to enhance colors in the context of low vision to help indirectly the visually impaired to identify the objects more easily in the scenes that are in front of them? So the main advantages of the use of the light is that there's no change in the world of presentation, unlimited field of view, and no device to wear. And also, we can imagine a smart adaptation of the device. We can imagine to adapt the light to the visual impairments. So here, we reverse the problem. It's not a patient that has to adapt to the system, but the system that can be adapted to the characteristics of the visual impairments. So to investigate this question, we carried out psychophysical experiments that was organized in two parts. In the first part, we asked participants to sort color samples. I will go back on this part just after. And in the second part, we asked the participants to locate one color sample among another set of colors. So here you have the general flowchart of the experiment. So you have on the left. So here, my battery is very low. So you have on the left the first question is based on the color arrangement, and the second part based on the color finding. So here we only focused for this pilot experiment. We only focused on the central scotoma. It means that the loss of the central vision for the patient, for example, due to an AMD problem, and we also limited the number of the channels in terms of light that we will mix to 3. Okay, so for the first part of the experiment, the goal was to determine the combination of the 3 best light channels that would maximize the color discrimination for the central scotoma. And the experimental setup was based on a 24 channels LED lighting system from Telelumen. It's a company that is based in California. And we also used central scotoma simulation goggles from Fock in the road, and also 20 Munsell color samples with exactly the same chroma and the same value. So you have a picture here of the organization, and for this first part, we only selected 13 channels of the lighting device. We rejected, for example, the channels that were in UV and in the IR because it does not participate to the color perception. And we had 16 live observers. So there were some simulation goggles, as I mentioned before. All these observers had normal or quality to normal visual acuity, and they also performed a color test just to be sure that there are no color blindness before the experiment. And so for this first experiment, the observers, the participants, were instructed to arrange 15 color samples. So you have, I said that we have 20 color samples. 5 of these samples were fixed. They were the reference. It's the samples that are with the point, the dark point here on the picture, and the other samples were presented randomly, and the observers had to arrange these colors under the different lighting conditions, the 13 lighting conditions. And after we reported the scores with the same rules as the Fans of Mansell 100U color vision test, and you can see here some examples. So here the degrees represent the circle of use, and the values inside just normalized values, the error score, and the 0 corresponds to the threshold between the good discrimination of colors, and under 0 it was a bad discrimination of colors. So here the color parts here on the plots are just here to mention the parts of the use that are correctly discriminated by the observers. So after that, after this first phase of the experiment, we selected 3 white lights, 3 combinations of different channels, and we selected the lights, the combinations that provided the widest area in terms of good color discrimination. So here, after selecting the channels, so here you have the number of the channels that have been selected for the light. We have to set up the relative intensities of these channels, and for that we try to find the best mixing, the best intensity that maximize the color rendering fidelity index, and also to enlarge, to have the widest color gamut area, and to minimize the DUV value. So it's what you have in this table. The different, so the 3 lights that we selected with the values, the maximum values that we was obtained in the different combinations, possible combinations of light. So here you have the 3 different spectrum that we obtained with this, the corresponding spectrum of the 3 lights that have been selected. And for the second phase of the experiment, so it was the idea was to test the effectiveness of these 3 mixtures. So here again, we use the same lighting system, the 24 channels LED lighting system, and to have a reference, we used phosphor converted white LED. It's very standard white LED panel that I use, for example, to illuminate offices. The same simulation goggles, and also now 8 test color panels that were based on natural color system, and so we have in these panels 24 samples and 23 samples with the same color, and just one sample with a different color, a very small difference in terms of colors. So we asked the observers to identify as quick as possible the color that was not the same inside the different panels. And under the 4 different lighting conditions, so the 3 mixtures that we selected, and the standard white light. So here are the results very shortly. So we can see on the table that we have the mixture L2 that induces the highest rate of the correct response. And we can also observe that the standard white light in the context of the visual impairment was not good in terms of color difference. And we have in the second table, we have the measure of the color differences in comparison to what the color differences that the delta E that we can have with the D65 illuminant. Okay, and just to add, we also observed the completion time of this of the experiment. So we can expect that the shorter the completion time, the less difficulty the observer had in finding the target color. And it also confirms the analysis that it's in correlation with the previous score that we obtained were reported in the previous table. And also we interviewed the different observers to know what kind of light they preferred, and the mixture L2 was preferred by 40% of the participants. Okay, to conclude, the first results that we obtained are very encouraging, and it seems very promising that we can use the light just to exaggerate the differences between the colors to try to help the visually impaired. Yesterday I presented so we obtained from this first result some prototypes of light bulbs, and these light bulbs were proposed to in a clinic of ophthalmology, and the first the first feedbacks that we obtained from the real low vision people are very good. So it seems very effective to use this light to facilitate the object recognition and the identification of the scene. That seems very interesting. So now with this first pilot experiment, we have a clear idea of what to do and how to manage the future experiments. So there are different questions that we want to investigate. So the first one is how many channels we have to use, because here we chose just to use 3 channels, but certainly it's not the best approach. Maybe it will be more than 3. Maybe also it will depend on the visual impairment. And how to optimize the light mixing, for the relative power between the different channels, and also to investigate other visual impairments, not only central scotoma. Thank you for your attention.